Thank you very much, Ashra. So it's a very easy presentation for me. First of all, because I will let the floor to our customer. So what is important is to understand what's happened on the field, how our customers are using that in our implementation, our 3D experience platform on the field. We have plenty of customers already starting initiative to be transformed on the manufacturing. We select 3 of them. Sorry for all the rest of the customer. We select 3 of them in 3 different industries. In aerospace, in automotive and transport and mobility, and another one in industrial equipment. And in 3 different locations. So today, I will be your travel agency. I will bring all of you, and we'll go to different countries, different places. So the first one, we will travel, that means to Seoul, to Korea. And we will have, that means a very, very strong customer working with us since some years now. It is a very, very nice product. So this company is Doosan. Probably all of you know this company. It's for construction equipment. It's for, that means the different engine, water power, different kind of industry inside. And they engage a very huge transformation in manufacturing. So the key message will be that means about how the product can be configured for manufacturing. So I will invite on stage that means Mr. Kim. It's a corporate advisor from Doosan Infracore. It's also the chairman of the Korean Smart Manufacturing Association. So very important people in Korea, very well known. So, and before that means to welcome him, I will introduce Doosan by a short video explaining who is Doosan. So please launch the video.
Doosan Infracore is the main subsidiary of Doosan Group and is the leading machine and infrastructure support business company in Korea. We build construction equipment, machine tools, engines, attachments, and utility equipment.
We have 14 operations and 5 R&D organizations all over the world, including Korea, USA, Czech Republic, China, and Norway. Doosan Infracore's R&D goal is to design anywhere, build anywhere.
We chose Dassault Systems because after reviewing solutions functionality, performance, and support strategy of the 3 global PLM vendors over 12 months period, we found that Dassault Systems' 3D experience platform and its industry solution experience was the best fit.
3D Experience Platform will provide a single source of truth that is necessary to support seamless communication within these R&D centers and 14 operations around the world. I am currently very much concentrated on the one-stop shopping of all the information. I believe 3D Experience can support my one-stop shopping strategy. For example, all the market information and sales order can be transformed to the engineering data, and those can be worked from styling design, engineering design, bill of material management, and up to aftermarket management within 3D Experience domain. The biggest benefit of this 3D experience is the alignment with solution to our industry. We have the goal to become global top 3 in the machinery industry by year 2020. To achieve this goal, a global collaboration has been an important project that enables us innovation management, cost control, and quality improvement. I believe 3D Experience Platform has been helping toward this goal.
So, Mr. Kim, the floor is yours.
Thanks, Jean-Marie. Hello, everyone. Hello, Shanghai. I'm Tae-Hwan Kim from Doosan Infra Korea. Where is my slide? Thank you. Well, today's topic I will present is digital continuity from engineering to manufacturing. Well, here is content for today, and let me start with paradigm shift. Well, we all know that the fourth industrial revolution is coming now. It is announced in the World Economic Forum early this year, and they say it will be coming toward us like a tsunami, changing everything, changing every system, way of living, way of working. So this is based on the technology revolution that merges physical world with digital world. Well, if we examine the history of the Industrial Revolution, you can find a key driver for each Industrial Revolution. For instance, steam engine for first Industrial Revolution that replaced the human and animal power, and electric conveyor belt for second Industrial Revolution that enabled mass production, and PLC for the third that led to automation. Then what is the fourth key drivers for fourth Industrial Revolution? It is so-called CPS, Cyber Physical System, which may not be so familiar. Well, this slide shows a good illustration to understand CPS and its coverage. The principle of CPS is like this. First, it collects, it starts with digitizing the real world using sensors, meters, even smartphone. And then it collects and accumulates the data from things using IoT technology. The data is now analyzed to generate the insight or intelligence. This intelligence is fed back to the real world to control the real world autonomously, making the closed loop cycle. Well, this principle can be applied to various industries like manufacturing, mobility, smart house, healthcare, etc. Especially when we apply the CPS to manufacturing process, we call it CPPS, Cyber Physical Production System. Well, there is a level in the CPS depending on the object. For instance, factory level CPS is composed of two CPS. Right-hand side is represents the CPPS, as I explained in the previous slide, which collects operating data from the real product and process in real time, whereas the left-hand side represents so-called PLM, which simulate product and process or factory using 3D cyber model before they come out to the real world. Well, the factory CPS or digital twin, I skipped the digital twin. Digital twin means when the two cyber physical systems, for example, engineering CPS, manufacturing CPS, are organically connected, then we call it, the digital twin. So factory CPS or digital twin can be compared to navigator. So right-hand side shows the data collection and analysis while it is operating, just like a CPPS. whereas left-hand side shows the simulation of function like PLM, which is needed when we set up the route in the beginning or when we meet some unexpected situation while it is operating. So in the navigator, those two functions are organically connected. Now let's examine the evolution of the PLM briefly. Well, PLM covers the whole product life cycle, from product beginning to end of life, as you know. The PLM is composed of 6 major components. The first one is product portfolio management, which includes MPD process, project management. Second, customer needs management. Third, product data management, a typical PDM, which includes BOM configuration, document, engineering change management. And the fourth is collaborative product development based on 3D CAD and simulation. Fifth one, direct material sourcing. And finally, the sixth component is digital manufacturing, which includes process planning, validation, digital assembling, plant layout, etc. But I would say in the era of Industry 4.0, this digital manufacturing will play a greater role because it will connect PLM with shop floor operation. As we all know that the PLM, 3D PLM evolved from 3D CAD from 1980s. And then it is now expanding to the shop floor operation by integrating production scheduling, optimization, manufacturing execution, and big data as well. Well, I believe this will truly enable the digital continuity from engineering to manufacturing in the future. Now, Doosan Infra implementation case of a 3D experience platform. Well, in the past, we had troublesome chronic issues about quality, delivery, and cost. We had massive engineering change even after a production, and we had repetition of time to market delivery and a higher material cost than planned. So to resolve these issues, we established the PLM initiatives consisting of MPD, virtual product development, new generation of BOM and configuration, and finally PDM. The main feature of Doosan PLM initiative is on the holistic approach. Well, it includes not only system implementation, but also standardization, process innovation throughout the whole product lifecycle. Our goal is to achieve dramatic reduction of engineering change after production and almost 100% accuracy of material cost and halved prototype validation period. Well, from now on, we will examine the role, the basic role of PLM, and then how we realized the role in terms of quality, cost, and delivery. Well, regarding the quality, 10th rule is applied to the unit cost of the issues which occurs along the product development stage. In case when we rely on the real product, as you see in the figure, many issues occur at the later stage of the product development, causing huge design change cost. To mitigate this problem, we introduce digital engineering, such as digital mockup, CAE, digital pre-assembly, digital pre-service. But this is not enough. This is from my experience. To have much more trial and errors at the earlier stage of product development, resulting in much less issues at the later stage of product development, I believe innovative process to support digital engineering should be involved. To do this, first of all, to secure design quality. First, we standardized 3D data quality, and the single BOM stretch was adopted for design anywhere, build anywhere. The sophisticated road cases for digital mockup, CAE, and the digital pre-assembly were developed. And also, the virtual validation process was introduced into MPD process. And also, some new teams were organized to carry out the new process. Well, regarding cost control, it is well known that 70% or 85% of cost is determined in the design stage, as the figure shows. But when we rely on the real product, the product knowledge gradually increase along the product lifecycle stages, causing impact gap in between. How can you reduce the impact gap now? I guess digital engineering and process innovation could be the answer. Well, early cost targeting and maintaining the target is very important in cost control. So we standardized design concept, system design concept, part design concept, the BOM structure for early collaboration, and also part costing table, which can calculate, forecast the design cost by manufacturing method. And also we developed a sophisticated cost process. Time to market. In the past, we had 2 batches of prototyping and a relatively long prototype validation period, occupying 2/3 of total product development period. To shorten the prototyping validation period by half, we took two-phase approach. In the front-loading phase 1, we reduced the number of the prototyping and batch of the prototyping, and then reduced the prototyping validation time by adopting virtual validation process in the early design stage. And then we developed and applied preceding development activities, such as platform development, modular development, new technology, or core part development in advance. To support the front-loading phase 1, all the time-related activities were standardized. For instance, drawing release time, part development schedule, prototyping schedule, validation schedule. And these schedules are included in the new MPD process. Well, throughout the holistic approach with digital engineering and innovative processes, we achieved a significant result, even though it is intermediate. So 47% of engineering changing after production reduced, and 98% of material cost accuracy was secured, and 6 months time to market was shortened. Now, I would like to demonstrate what it achieved and how we realized the digital continuity through the 3D experience platform. The demo will contain login to 3D experience, managing standard and option, retrieving configured model, design automation, and the view EBOM and the 3D in the web, creating MBOM from EBOM, and the routing, allocation, check build-up, and time analysis, finally creating work instruction. This is the video. Well, thank you. It is a short video, but it is not interfaced operation. It is integrated operation by 3D Experience platform. Well, I think I finished earlier. Well, last slide for concluding remarks. Well, 3D-based end-to-end engineering, which is one of the three axes in Industry 4.0, is essential for the factory CPS, that is digital twin. 3D Experience platform proved, as you saw in the video, to support the seamless integration from engineering to manufacturing by providing a single source of truth. Tucson Infra Core successfully implemented 3D Experience platform through the holistic approach, not only for system approach, but also for process approach. The next step is to deploy CPPS on the shop floor, to converge the CPS with the 3D Experience platform to complete the digital twin in the future. So this is all I have for today. Thank you very much for your attention.